Hello everyone. So over the past few tutorials, we have been trying to make a simulation of this industrial robotic arm. Its name is GP27. It's from Exaba Robot. So we've been trying to simulate it on ROS. I'm using ROS Kinematic under a virtual Ubuntu. So let's see. What we are going to do is we are going to make the MoveIt package for this. So in the last tutorial, we configured tutorials and we configured ROS control, and before that, we see how to use them. And they are on my Git repository. So what we did last time was basically we wrote this control gazebo file, and we know how to and we configured a joint trajectory controller named arm controller, and we can run it, of course, if we go back to our Catkin workspace. Catkin make, you don't have to do it, but source it. And if we run, for example, GP27 visualization control gazebo, and yeah, it's gonna take a while to open up, but as you can see, loaded the gazebo plugin for control, and it will load everything in a minute. And if we check ROS param list, grab control, we will see that the controllers are in the ROS parameter server. This is the controller that we are going to load, arm controller, which is a joint trajectory controller. And one way to see if it's working or not, like I should have told you this in the previous tutorial, but like for example, as ROS topic, there are ROS services. So in ROS services, what you can do is basically you can get the state of the controller, for example, from the list controllers service. So ROS service list GP is the name, GP report, and controller manager. So GP report is the namespace that we have been using throughout, and we used it in our this controllers. We have used it in our URDF. We've used it in our control config file. We actually do need to do ROS service call, not ROS service. And because the service request is an empty message, that's why we don't need to fill out any message here. So you can see there are two controllers: joint state trajectory control, joint state controller, which publishes joint states in our ROS topic, and under the namespace of GP7 underscore report. Then we have arm controller, and it's basically controlling the arm. It's not just publishing the state; it's actually controlling the arm. It's a position controller, and it's a trajectory it's a joint position trajectory controller, and it's running currently. We can also stop them, do crazy stuff, but one last time, if you don't want to write any program and just want to control it, you can use RQT joint trajectory controller controller. This is sort of like an RQT plugin which connects directly to the controller manager from ROS control. So we'll start with the raw MoveIt. I just want to make sure that everything is working properly before we start. So these are six. We have six joints in our trajectory, and we can select from the drop down. Sorry, excuse me. The control manager and arm controller, and then we can start it and change the position. So these sliders basically limit themselves from the minimum and the maximum position that we have mentioned in the URDF before. So basically it works very smoothly, but because I'm running virtual Ubuntu, so that's why it's a little bit jerky. And yeah. So this is well and good, but the problem with ROS controller is that we cannot do pose control. So for example, we do not know what is the pose of the AND effector or joint 6 AND with respect to base. We basically know it using the TF tree, which we can launch from TF tree TF, for example, TF echo. If I want to know link, so remember, every coordinate frame is attached to a link. It's not a joint. Joint is not a physical quantity. Link itself is a physical quantity. It's like it has mass and everything. Joint is just a concept of axis around which the link move. Two links are attached virtually by a joint. So if we want to get the pose of, for example, 6 link with respect to in the coordinate frame of link 1, we can do this, and it will start publishing the translation and notation. So for example, it's the link 6 frame. The x-axis of the link 6 frame is currently 0.505 meters away in the x-axis of link 1, and link 1 x-axis is basically the same as the base link as far as I remember. So what you can do is, if for example, if we change any of the links, so they are because it's a chain or serial robot, so when you will change this and the robot moves, so the 6 frame will move and its position with respect to link coordinate frame 1 will also change. So any moment now. Come on. Okay, so I don't know if you see either it changed or not, but currently it's this. So I'll move it somewhat more. Move it. I'm sure I'm doing something wrong because it's not changing. It usually change. So let me TF echo. Let's do base link because it's a fixed link, and link 60. The value should change. It's not changing and it's confusing. Well, so it usually changes, and I'm sure there is something wrong, something going on here. But let's skip it for a minute and talk about MoveIt. So what's the point of using MoveIt is basically, for example, if you want to do a pick and place task, it's very difficult to do it with joint positions. So you have to know exactly what joint positions you have to go. And because it's in joint space, so it's very difficult to, either you have to make your object bring into the joint space, which is almost very difficult, or the other way is that you tell, which is like an inverse kinematics task. So one way to say it is basically, if you are using MoveIt, it's very easy to use inverse kinematics because MoveIt usually sort of adds inverse kinematics plugin in it. So let's start making a package. So I'll first close everything. So to make a MoveIt package, what you need is basically a URDF. A proper URDF is ROS controller. So if you're using simulation search, you're gonna need visible ROS controllers, and you cannot not use any ROS controllers. Basically, you always need joint trajectory controllers. They can be of position type, velocity type, or the third one, torque force type. So you cannot use single joint controller. So first, if you do not have MoveIt, what you can do is you can install it using ROS Kinetic. So if you have Melodic, so Melodic, and then MoveIt. So there are a lot of the packages for MoveIt. So what I'll do is I'll show you which ones to install. Basically, it doesn't matter if you install all of them. It does not. You just do this and it will install everything related to MoveIt, and you won't have to install every single package separately. Then once you have installed it, what you can do is you can launch Setup Assistant, which is very easy. You do ROS launch. It's basically a node. So ROS node. So you can do ROS launch, MoveIt, Setup Assistant dot launch, and hit enter, and it will start launching a GUI. So this GUI is very convenient to make ROS packages, and I'm sure most of you have seen it before. So to create a new package, you click on create new MoveIt configuration package. In the browse file, you go to your URDF. So basically, I'm in your tutorial workspace, source, GP7, visualization, URDF, and this is the URDF that I'm using, not the simple one. So I'll load this, and okay. After doing that, you can just do load, and if you just expand this window a little bit, that will make it come on. So it little bit hangs, so I stopped recording the video. So now you can see that we have this report, and yeah. So the first thing that we have to do is basically do this collision tag. You can read on what it is basically. So it checks for collisions, and how it checks is basically, remember we talked about it, that meshes are used for collision checks, and STL files are basically simple numbers that define these meshes. So if two links are connected, then collision check has to be turned off between them, otherwise they will always be in collision. So MoveIt always checks for collisions when they are planning. So they have to, this package has to know that these two, for example, link 1 and 2 are in collision. That's why I have to generate this collision matrix. So I'm gonna do it for low sampling, but you can do it for high sampling. So as you can see, it says that base link 1 and link 2 are adjacent links, so they will always be. So the collision check is disabled for them because they will always be in collision. Similarly, link 1, 2, 3, 4, 5 like this. It's almost not possible for, like, they are not, for example, link 1 and link 6 are not directly connected. So if they are colliding, so it does not mean that they are colliding because of how they are manufactured and how they are assembled. So it means that it's somewhat user mistakes, and it has to be avoided. That's why it says, for example, link 2 and link 5 are never in collision. So that's what this window checks for. Virtual joints is something that we're not going to talk about right now, but it's something that's used for higher degrees of freedom robotic arm. Planning group is one of the most important thing in MoveIt. So for example, you can it's like trajectory controllers, in the sense that, for example, if in a trajectory controller you have 6 joints and these joints are controlled simultaneously. Similarly, planning joints is almost the same thing for inverse kinematics. Like, it's not the exact same thing, but like you can think of it like that. For example, you can have multiple planning groups. So for example, you can and in each planning groups you have certain number of joints, certain number of links. So because we have only one complete robotic arm, I'll make this as a one planning group. For example, if I had a gripper in front of it, so that gripper will be another planning group. And if I had, for example, two, like a humanoid robot with 2 arms, so each arm would be one planning group, something like that. So because so it's a concept in MoveIt. So just make it a little bigger. And the first thing is group name. So I'll just name it arm. You can name it anything you like. So this kinematic solver is basically that inverse kinematic solver that you have to select. So there are multiple of them. Most famous of them are basically KDL, which is Kinematics Dynamics Library, and it solves the inverse kinematic using optimization and numerical method. So it's very slow. Then we have TrackIK, and TrackIK is basically the most popular one and most fast one. We have one more. I have not actually used any other one because they are sort of like spin-off of these main libraries. But there are, for example, TrackIK, and then there is one which is called FastIK. And the difference between FastIK and all these libraries that FastIK basically uses like algebraic equations to solve the like it finds the algebraic solutions for your robotic arm. For the forward like inverse kinematic solution, it finds that algebraically instead of numerically. And then once you have the equations, it's very easy to just substitute the joint values and get the pose or the XYZ value of the end effector or the tool. TrackIK is sort of an amalgamation between like two KDL. One is the KDL library and there is another one. So it uses that, and it's much faster than FastIK and KDL. So I'm going to use KDL. And then there are other parameters that you don't have to change basically. And for group planner, so group planner, there are a lot of planners, and there are some that's going off the screen, but the one I'm going to use is RRT. So these planners are basically the one that uses, for example, if you give your certain pose and your certain pose, by pose I mean the position and orientation of the tool with respect to the base, and you give it to, if you ask the robot to go from this pose to another pose, so it has to plan. And there are different planners. So each planner, what they do is basically they convert these poses into inverse kinematics, and from inverse kinematics they see that either like joint 1 or joint 2 are not in that position where it goes, where they are not out of the limit and stuff like that. So one of the fastest one in my experience has the one that always works almost is RRT. I'm not sure what it stands for, but do look it up. Next, we have to add the components of the group. So because we are going to only make one group of this, so we are going to start with adding joints. So it's like this. So I have to select all the joints because it's a series robot. So I'm going to select all of them and just click this, and it will come into the selected joint coordinate here. So then I'll save it. Similarly, I have to select links. Actually, it's not important to select links, chains, and subgroups, but it's always good to do things properly. So select links and edit selected, and then it's basically the same. So link is, because it's a serial robot, so you select from base link to link 6. So for example, if there was a gripper connected, so there would be a gripper base joints, gripper right finger and left finger, and I would be selecting that for the gripper group, but we don't have it here. Probably in some other tutorials we'll add gripper also. And chains are basically the serial parent-child relationship between each link. So what we do is basically open it completely. Because you cannot have cyclic chains in any URDF. Even if you try to write it, it will give you an error. So by cyclic, I mean that for example, link 6 cannot be the parent for link world 1 or any of the above link, because it will make a cycle in the parent-child relationship. And URDA can only be robots. So you have to select the base link, which is sort of like a parent link. So either select this or base link or world 1. They both are the same coordinate, if you remember from the URDF. And for the tip link, I'm going to select link 6. Now the cool thing about this is, for example, sometimes what happens that you don't want to select link 6, you have another coordinate frame which is like an imaginary coordinate frame, which is, for example, 2 meters forward from the link 6. So you can add that frame into the URDF, and then you will select that link here, which will be whose parent will be link 6, And what will happen is that once you configure this MoveIt and you try to find the pose of that link with respect to the base link, you'll get exactly the same pose. So this is one cool thing about it. Okay. So I'm gonna save it. Now there is subgroups, but you don't have to do it if you do not have like a humanoid robot. You don't have to configure it. As for robot poses, this is also a very cool window, and you can have pre-configured robot poses, and it's easier to bring the robot to that pose. So, for example, one of the most common one is home pose. That is almost in every robotic arm, where the joint values, joint positions are all zero. So I'll select that planning group because I'm only using one planning group, so it's gonna be arm. And remember, we named the planning group arm. That's why it's arm. And I'll save it. And just for the sake of it, I'll add another pose so it's easy to see. So for example, stand up is one pose where the arm is completely standing up, like this part is going up. So to do that is basically joint 1, 2, 3. I think 3 joint is to be a little bit up. So because it was at 0 as a 90-degree position, so if I add 1 point, what's the value of pi? Shit. I forgot. Oh, great, now I've opened 1 minute. So I went back and looked at what the value of pi is. It's 1.5707. And if I do this, it will stand up perfectly. You can see. Now you can rotate it in this window. It's basically a 3D view window, but I'm not going to because it's fine. So stand up is another pose, and you can select it. And we have end effector. End effectors are basically clippers, and we do not have it, so we'll leave it as it is. Passive joints, similarly with passive joints. Passive joints, ROS controller, we are going to configure it ourselves. Simulation, it will generate the same URDF, but like it will be much pretty. So it's okay. If you have a camera, you can do crazy thing here where you can set up perception for point cloud and depth map. We don't have it, so later on when we add camera in this robotic arm, we'll edit this MoveIt setup. Then you can do author information where you add your name. So I'm gonna do Arshad and shouldn't have done that in a video I'm gonna put on YouTube, but that's okay. And the final thing is this. So these are the files that's going to be auto-generated for us from this MoveIt setup assistant. It's very nice because so the path, we have to define the proper path and before clicking on anything. So we are under tutorial workspace under GPS here, and like these files will be written in a folder. If I go under this folder, so there is this folder, and there is this convention that, for example, the robot name for us was our robot name was GP7, I think. Confirm it first. So if I go under URDF, the robot name is basically GP27 robot. So what you should do is always name your package as GP27 robot MoveIt config. You'll see it's very common that robot name underscore MoveIt underscore config is usually the MoveIt configuration package. And under this package, I should go back. Select this and then we can do generate package. and it will ask you that no effector have been added and no virtual joints have been added because we don't have them in our report. So let's do this. Once it's completed, and you can just simply exit the setup assistant. And just remember that in any time in future you're going to you can edit this package from setup assistant directly from the files. One thing I forgot to mention is that when you open ROS launch MoveIt setup assistant, you have to launch it basically from the tutorial workspace, because most probably your tutorial workspace will be source, and that's important because when you load your URDF, it basically looks for those meshes files, and if your workspace is not source, then it will give you error. So always either source your workspace and then open the ROS launch setup assistant, MoveIt setup assistant from that terminal, or do this like the way I did it. Now we have, if we go under here, we have this MoveIt files, and the way to, there are two folders. One is config, which has all these files, and the other one is called launch. There is this very cool demo about it which we can run, but I always like to, it's always professional to have another package that launches this and bring up everything. So what I'll do is I'll go into my source folder, and I'll go into my meta package, and under this we have all the ROS packages. So I'll create a create package, and I'll name it GP7 robot bring up. It doesn't have to be, and under GP7, GP7 robot bring up, I'll create a directory called launch, and under directory what I'll do is I will create a file called GP7 bring up .launch. That's right. Okay. Now most of the things that we did in so here's this file that I created, and it's a launch file. So I'll do launch file. So basically, first what we have to do is we have to things that we were doing previously. So we have to launch the launch Gazebo, upload our URDF to the ROS param server. Then we have to spawn the URDF into Gazebo. Then we have to spawn controllers and upload the controllers into ROS param server, and then upload them to controller manager. We have to do that. We have to do all of that. So instead of doing it again, what we can do is basically call this launch file, which we have under visualization, and under this control launch file here, right? So I was thinking, so because one way to do it, I left very quite fast, is I just copy any launch file. So this is the way you include a launch file. You basically call one launch file from another launch file. So the package name is GP7. Oh shoot, name it GP27. Okay. It's going to be a mistake, but you should name it GP7 and not GP27. So it's okay. It will take me a lot of time to remake it, but it's okay. So visualization. Come on, it's in the package. So under visualization launch package, we have this control Gazebo file. So I'll take this Gazebo file, and if I look at this Gazebo file, it does not take any special arguments here. So we can remove this are, and like I'll show you what I meant. I'm basically using this bring up this launch up 7 GB 7 underscore bring up to launch control gazebo only right now. So for some reason I have this habit of sourcing the workspace again and again, but you can do GP7 robot bring up launch file, and you'll see that the same things will open up, should open up. Now why I did it is because in this launch file I will also include like MoveIt group. So MoveIt will also start from this launch file instead of using the launch files that were auto generated from the setup assistant. It gives you a better understanding of how MoveIt is working, or in fact like not like deep understanding, but from the like superficial understanding. But you can like it will start the same thing, but I'm just gonna stop it for now. So if we go under this robot MoveIt config file and under launch, we have this demo launch, and if we see there are a lot of things here, but the main launch file is basically the planning context, and General Publisher we already do that. There is some MoveIt, ROS, and Move Group, right? So this I'll copy this file, I'll add it here. MoveIt, run the main MoveIt executable without registry execution. We do not have the controllers configured by default, so we will do this, but not in this video because it's almost getting 30-minute video. So I'm also going to remove this because these are the same arguments. Let's see if it works. Oh, one more thing. I will also launch ROS so it's easier to see where it is. And one reason I did not change this name now, because I know that I should have put GP27 instead of 27, is because everything is now connected like this. So I'll have to change everything from here. Other choices, I delete this folder and do this again, the configuration from the setup assistant, but for now it's okay. So this is all, and okay. Because we are not taking any argument here for debug, so I'll remove this debug and it will take the default value, and let's see. Oops. Like it's been almost 6 tutorials and we have not written any programming to like we have not written any code at all, and we have a robot that simulates. So this is something very cool about what I find very cool about ROS, that you almost get any package that you want and it works out of the box if you have configured it properly. So I will resume the video once it's properly started. Yeah, so this is basically ROS with MoveIt configuration, and we have the physical simulation running in here, and this is just visualization. So now the cool thing about it is I move this because ROS controllers are still not configured to work with MoveIt, so it will probably not work, but it will hang a lot. So I'll probably make the next video in a dual boot environment. So one thing is this: you have the scene geometry, scene robot, planning request, and all that, which is not working right now, but for sure in the next video it will be working smoothly. So for now, yeah. So you see that here you have this planning group, and it's the name of our planning group, which is ARM. One important thing, if you go under motion planning and planning, here is the RRT that we selected for the planning library and as a planner for our ARM group. If you go under planning, and if you go under this select goal state, it says random state, and if you click here, and it will take like to open up. Yeah. So we have two predefined poses, home and we have two predefined poses as home and second one was stand up, I guess. So here they are. You can select them and then click on plan and execute, and it will go to that, but currently it won't go to that because we don't have the ROS controllers, those trajectory controllers connected with the MoveIt. We haven't done that part, so we will do that in the next video, and then it will work like a charm. And there are other things that you can explore in here, which we'll probably do in the next video. So until then, have a good day, bye, and subscribe to my channel if possible. Thank you.